Hybrid weights keep breaking because your scores are not comparable. Calibrate them once and stop retuning. You will walk away knowing why score scales mismatch, how to turn raw signals into comparable probabilities, and a simple fusion rule that stays stable across queries. I'm Professor Pi, teaching search and IR with simple Python. Many search systems mix a lexical signal like BM25 with an embedding similarity. That hybrid can be powerful, but people constantly tweak weights because the numbers mean different things. One model might output values around 3. The other gives numbers between 0 and 1. You then chase a weight that works for one query and breaks on the next. Calibration solves this problem by converting each signal into the same evidence space. Success looks like a single rule that picks good results across queries without per-query weight fiddling. That makes tuning faster and systems more robust when queries or data drift. At a high level, we will map scores to probabilities, then combine evidence additively. Imagine 2 lists of numbers, one from BM25 and one from Embeddings. We fit a simple curve for each, so both become probabilities. Once calibrated, we can add them in log odds space and get stable hybrids. Strengths are interpretability and stability. Weaknesses are that calibration needs some labeled examples or reasonable priors. We will build a tiny toy that shows the whole flow. It uses 3 documents and 2 sets of scores to mimic BM25 and embedding matches. We fit a fast Platt-style calibration on the BM25 side, pick simple parameters for embeddings, fuse the calibrated signals first by averaging, then by a more stable log odds sum. This keeps the code approachable and shows the key ideas before you scale up. Now we will set up the toy scaffold. This snippet sets up 3 toy documents and 2 score lists to mimic BM25 and embedding similarity. The variable docs names the items, while BM and EMB hold uncalibrated relevance signals for each document. The index BI is computed by taking the position of the highest BM25 score using the built-in list indexing function. The variable EI similarly captures the leader under the embedding scores, though we do not print it yet. This minimal scaffold gives us 2 incomparable scales to calibrate later. The printed document identifier shows which item currently wins under BM25, establishing our starting point. Next, we fit a quick Platt-scale for BM25. This code performs Platt scaling for BM25 using NumPy to avoid iterative solvers. The array XB holds raw BM25 scores from a small labeled set, and YB contains binary relevance labels. The variable TB clips labels to avoid infinite logits, and ZB applies the logit transform to create a regression target. The design matrix stacks XB with a constant column, so ABM acts as a slope and BBM as a bias. The function numpy.linalg.lstsq solves for these parameters in one step. If you increase the clipping, e.g. 0.05, the fitted slope shrinks and probabilities become less extreme. The printed slope indicates how sharply BM25 scores map into probabilities. Now we will convert both signals into probabilities and try a naive fusion. This example converts raw BM25 and embedding scores into comparable probabilities and fuses them. The probability PB uses the previously learned ABM and BBM passed through a NumPy sigmoid for each document. The variables AM and BM set an embedding sigmoid that maps cosine-like scores into probabilities PE. They represent a quick fit or prior calibration. The variable fuse averages PB and PE to form a simple hybrid signal, and top selects the highest fused document. Increasing AM steepens the embedding calibration and gives more influence to high cosine matches, while decreasing it softens that effect. The printed identifier shows the winner under averaged calibrated probabilities. Next, we make fusion more stable by working in log odds space. This snippet switches from averaging probabilities to summing weighted log odds for stability. The weights WB and WE use the absolute slopes from each Platt model, making steeper calibrations contribute more. The variables LB and LE convert the calibrated probabilities to logits, aligning both sources on an additive evidence scale. The fused logit combines WB times LB and WE times LE, then PF maps back to a probability. If you increase WB relative to WE, BM25 evidence dominates. The reverse emphasizes semantics. The printed probability for the third document shows a confident, calibrated middle case under the robust fusion. Finally, we simulate query drift to check stability. This code simulates drift by changing both BM25 and embedding scores for a new query while keeping calibrations fixed. The variables new BM and new EMB reflect shifted signal strengths, and PB2 and PE2 recalibrate them with the same Platt parameters. The fused PF2 applies the same weighted log odds rule, ensuring consistency across conditions. The variable SUC averages success at rank 1 over the original fused winner, and the drifted scenario using simple relevance arrays. Lowering, we would reduce embedding influence under drift, potentially changing the second decision. The printed average success shows how the calibrated, stable fusion behaves across two conditions. To map this toy to a production case, replace the three documents with a real corpus and the toy labels with a small validation set. Keep the same calibration step, but fit it on a representative sample. Use an ANN index for embeddings and compute BM25 from your search engine. The fusion rule and weights remain the same. Only the signal sources scale up. Recap: it is a small calibration step that turns different score scales into aligned probabilities. Use it when you fuse lexical and semantic signals and want stable weights across queries. Caveat: you need representative labeled examples or sensible priors. Otherwise, calibration can mislead. Next step: tune BM25 K1 and B on your validation set while keeping the calibration fixed. If short, practical IR helps, subscribe and watch the IR videos.